All right, guys, we are in for a treat. Sorry, I'm not able to join in person, but we have Vinija Jain. Uh, she's a staff engineer at Google. Earlier, she was working at Meta, and she's working right in the trenches, working on agents as part of the Gemini. So I don't think we could have found a better person to talk about this topic. Um, Vinija publishes regularly and frequently, and many students have been mentored, or and she's collaborated with many people. Um, so feel free to ask questions. She'll welcome that. And on to you, Vinija.
Thank you so much, Dr. Shade, for that lovely intro. And hey, everyone. Excited to see you all. And let me start sharing my screen and we can get started. All right. All right. Let me know if my screen is visible and you can see the slideshow.
Yes.
Okay, perfect. Thank you so much. All right, so today what I kind of wanted to cover was the rise of modern AI agents. And just to give a quick intro on myself also, I'm Vinija. Like Dr. Shade said, I work at Google currently. Prior to that, I was at Meta, and I do also publish frequently on LLM and related topics in multiple A-star venues. So excited to sort of delve into this topic. And afterwards, happy to take any questions. And also if there's anything that, I wasn't able to answer, happy to take it offline as well. All right. So the way I wanted to kind of start this is by talking about that agentic AI moment that sort of everyone has probably experienced within the last 5 or so years. And for a lot of the folks, that whole moment was around the time of the release of ChatGPT, when the system's capabilities kind of exceeded the expectations of what we had for it. For example, when ChatGPT came out, it was just so phenomenal that a simple transformer decoder model, which is just looking to do next token prediction, is able to kind of take that and correlate it down to so many multiple tasks like sentence completion, summarization, mathematical calculations, essay writing, blog writing, refining grammar, just so many endless tasks with just one loss and one training objective. That was just phenomenal to see. And I feel like we're having that moment again with agents where we're able to see their capabilities of doing so many different task executions that was beyond the realm of imagination. For example, there's quite a few agents out there already. There's Cursor, which is a code-based agent which you can just prompt and it will not only generate the code like you can in ChatGPT, it will actually form it within an IDE setting and help you run it and see it live. That's a pretty phenomenal thing that I think we're getting to experience. So that's kind of how I wanted to start this. Now, let's kind of delve into the meat of it by first starting to define what AI agents are and just kind of outlining the foundations of them. So typical LLMs and how they differ from just, typical LLMs, there's no clear definition of agents, but there's a few key components that needs to exist for a system to be called an agent. So typical LLMs just generate responses in a single pass, and they have zero-shot interactions. And when I say typical LLMs, I mean LLMs that are just the base model that we no longer see anymore, not LLMs that have gone through SFT and are able to do multi-turn conversations. So the base model is just looking to do next token prediction. So next is just looking to predict the next token based on what it was fed earlier. Now with SFT, it's able to do multi-turn conversations, which we're able to see with ChatGPT. And that's the typical LLM setting. It does a sort of a single pass edit and What it's looking to do is a simple LLM is not looking to refine its answer. That changes in the agentic framework. So there's another big topic that we're going to talk about here, and that's agentic workflows, which if workflows in agents follows a structured, iterative, and it could be a multi-step task process. Um, Workflows are different from just general agents in the case where workflows are defined more clearly. So there's a very clear set of steps that need to be executed, and the autonomy is not given to the agent as much. So the steps for workflows, and steps for agents in general include planning, drafting, reviewing, and refining the outputs. And the cycle it will keep going through will help improve accuracy. It'll help improve the output. Over single attempts rather than having to iterate on it multiple times. And it reflects more like a human dynamic in this refinement process. So just looking at the diagram here, this is a very high level structure of what an agent system can look like. It starts off with the agent core. The agent core is the brain of the entire system, and this can just be a simple LLM that's basically looking to figure out what execution to do based on what query the user has given the agent. So the user, as we see on the left here, the user requests something, it goes into the agent core. Now the agent core needs to decide what the next step here is, whether it goes into the memory module. And memory here, I mean a database, a vector stored database, anything where we're able to or even a cache system, where we're able to pull from memory for something that the user has asked for and retrieve it back and sort of send it back to them. So this could look like even a retrieval augmented generation system, a RAG-based system. Or the agent core can figure and can think that it needs to call a tool. Maybe it needs to call an API. Maybe it needs to call some network security. Maybe it needs to call a code IDE to be able to run the code and execute it and refine it before sending it back to the user. Or it can go to the planning module where you'll basically take the tasks that the user has given you and break it down into several different planning tasks and execute them either serially or parallelly. This is very similar to the way humans work. You can think of, as you get a task, maybe you take a post-it note and you write down all of your tasks that you have to do. As humans, we're very good at serial tasks, but as a machine, what it can do is execute in parallel as well. So if the user's looking for a research-based problem, it can, plan out to look at different websites. Maybe it can plan out to look at its database and pull out, retrieve all of that information for the user, and have it sort of back to them. So that's just the foundations of AI agents. And now we're going to sort of dive deep into each of these elements that we've talked about here.
Vinija,
Yeah.
I have one question here.
Yeah,
So
go ahead.
we're talking about, if we can go back to the previous slide.
Yes.
We are talking about agent core, which refers to the large language model, right?
Yeah.
For processing. So
Right.
where does that orchestration comes into picture? And then that's my first question. And then if you think about the second question, like in the planning module, so does it convert that into a PDDL format so that I may have several questions asked in the, you know, kind of comprehensive answer, one question there, so that how does that planning kick in to make sure saying that I'm going to break down into subtasks and stuff like that. If you're going to explain this in the future slides, I'm totally fine.
No, absolutely. That's a great question. And I can help sort of expand on that here as well. So how does orchestration work? There are two components of this entire system. One component is purely software based, and one component is mostly machine learning based. The kind of what I talked about is more on the AI LLM side. The entire orchestration, how it works, that's just pure software in the background. You can have, frameworks like LangChain, LangGraph working to help take out the output from the agent core to take the user's request, prompt it into the agent. Actually, there's multiple steps that even go before that, where you will need to refine the query. You'll need to make sure it passes through a different filtering criterias. When the agent core is looking to respond back to the user, it also needs to go through multiple filtering criteria to make sure that it's safe, helpful, it's harmless. So all of those pieces are basically software fundamentals working in the background to help the execution of all of these. Now, because I mean, there's so all of these components could be LLMs on their own. And there's no way for an LLM to interact with another without an execution layer in between. And that could just be something simple as even a microservice. It depends on how you want to create your application. The planning module, again, could also be an LLM, or if you have something that is very streamlined and not as open-ended, you can also create a sort of service around that and say, my ecosystem here only takes 4 tasks. So these are the 4 tasks that I need to plan. And in terms of that, maybe you don't even need a planning module. What you can do is say you only have 4 tasks and the user is asking task 1, then the agent core needs to go and route to this tool. If the user is asking for task 2, then the agent needs to go to the memory module. In that case, you can prompt the agent with a few shot examples in its system prompt itself and tell it, in this case, execute that, and you may not even need the planning module. So this is not a very strict design adherence. This is sort of a general design of how it's works most of the time. Does that kind of help answer that?
Yeah, yeah, thank you.
Awesome. Perfect. All right, so now I kind of wanted to delve a little bit deeper into workflows versus agents. And the definition I'm using here, I've taken from Anthropic's blog, and I'll share that as well. So workflows, like I mentioned, are predefined code paths with orchestrated LLM tool interaction. So this is something like what you were looking to ask earlier here. Um, this versus agents are very dynamic in how they decide which tool to call and how to manage tasks and how to plan. So you can think of 2 systems here. One system could be, say, it's a customer support agent. We've seen this often in different use cases. And you're going in and maybe it's a chat-based customer support or even a call-based. And you're going in and if it's a utility service company, you're asking, my electric has gone out. When is it going to come back? That's a very workflow-based agent because you understand the user's query through your planning LLM. And what you need to do is basically the user is asking when their electricity is going to come back up. That should be a simple API call, a predefined code path with an orchestration. You query that API with a lot of the metadata that the user provides when they log into your chat-based system, their location, their account number, their name, any other details. You populate the API call with all of that, you retrieve the information, and you send it back to the user. This is a very not open-ended use case, and this would be called a workflow. There's only one correct API call for this situation. Now, think of another situation where someone is looking for a more maybe helping to curate a research paper, or maybe they need help with their thesis and they're stuck on something very specific. Now, this is a very open-ended problem because say they're asking for a difference between 2 different theories. The agent can decide to maybe query multiple different websites and get that information from there. The agent can decide that, oh, we may have this information in our database, and it can look to, query that. Or maybe you even have a multi-agent system where there's a different agent that's very specialized, and maybe it's even fine-tuned in this niche and in this domain. And the agent chooses to call that agent to get that information and then respond back. So that's a very open-ended system there. So workflows here are deterministic. They're optimized for predictable and repetitive tasks. Whereas agents kind of have to demonstrate autonomy, adapting to, different changing goals or environments. But they're both broadly categorized under the agentic systems by researchers. So this is kind of getting more into the definition of what an agent is. Now, you may be wondering, why do we even need agents for a very predefined structure, like say, when is my electricity coming back? That's because when the end customer chats, their query can be very vague. It could be multifaceted. People talk in different ways. If it was a very structured conversation that the user, only types this specific sentence, and then we kind of trigger that API call. That's a very simple system to build where we only have one use case and only one happy path. That's generally not how people operate. They can ask multiples of maybe 5, 6 questions. When is my electricity coming back? When is my payment due? Why was this charge done on my account? Multiple questions at once to customer support. And that would still be categorized as a workflow because the output of that is still a very predefined code path. But this is why we need the planner agent to begin with, because we need it to help translate all of the questions into the different API calls or the backend tool it needs to call to be able to give the answer back to the user itself. All right. So these are taken from Anthropic's blogs, kind of delving deeper into workflow agents itself. They've categorized 3 different workflow agents. So the first one is a prompt chaining one. And you can see basically prompt chaining, what it does is it decomposes one specific task into sequence of steps where each of the LLM call process the output of the previous one. So it's dependent on the previous one, which is why it needs to be in a chain. You can add like different gates and checks to kind of make sure that the path is going through the right way. So in this case, what they have is, it starts at you make your first LLM call, you do your first check. Maybe your check could be, is this user even a customer of ours? And if that passes, then you go to the second check where maybe you need to make sure that their accounts are valid, or if you have that information, and then maybe the last API call is for to the LLM is more for filtering or other criterias, and then you can output. And if the first gate fails, then you simply exit and you don't have to go through the multiple other API calls there itself. So this is the first way you can arrange your workflow system. This is prompt chaining. Um, yeah, so this is prompt chaining. Now we have parallelization as well. Basically, LLMs can work simultaneously on a task. And instead of having to do it sequentially, like we said before, we can do it kind of in a parallel way here. So the output is aggregated at the end. And this workflow basically, and its parallelization kind of manifests in these 2 key variations. So it's going to have sectioning and it's going to have voting. And sectioning is going to take the in task that it has and break it into independent subtasks that will be run in parallel. And then voting is going to be running the same task multiple times to get diverse outputs. So you can think of maybe, someone is asking for a very creative writing piece. There's multiple ways to kind of execute that. So in terms of that, what they can do is maybe the first LLM call can say, write this essay or something in a Shakespearean tone. And the second way they can say, write it in an XYZ tone. And then basically an aggregation and a voting can figure out which of these which of these outputs, and how do we diversify this output and then give it to the end user. And this can also be sort of steered through how the user asks for the question. But if there's a very specific path to this, it can be very predefined, and then multiple LLM calls will basically section out the task and then aggregate it through the end. All right. So next, what we'll look into are the different components of the agent framework. So what we saw earlier was a very high level kind of architecture diagram. Now here we can delve a little deeper into this. And this was from one of the agent survey papers. Would highly recommend going through that as well. It's very educative. Okay, so the agent core that we saw earlier, that is basically the LLM that we have in the middle, and it's you can think of it as the brain, you can think of it as the primary decision making, and kind of a dynamic task manager. It's looking to understand where to go from here. It's looking to execute. It's looking to make the calls. It's looking to interact with the end user. The memory modules that you'll have will support the short-term and the long-term information retention. So you can think of the brain memory modules here where you'll have storage. Storage is basically, any type of database that you have that's predefined for all of the content. Now, memory doesn't always have to be stored. It can also be knowledge that can be retrieved. And knowledge can be retrieved through looking through either websites or looking through maybe talking to other agents or any other place where it can sort of go to find the specific knowledge that it needs for this task alone. And then tools will provide it specialized abilities. You can have, APIs and workflows, which we've talked quite a bit about, and then planning module basically enables the task decomposition and structuring the problem solving system. So in this, what we have is the agent comes in reasoning from so this is a weather-based problem scenario where the person says, look at the sky. Do you think it will rain tomorrow? If so, give the umbrella to me. And this is a very futuristic agent architecture where this agent is not just software based, it's actually physical. So it's a physical robot that can come and do all of this execution and then hand the umbrella back to the itself. So what they're saying, the brain will basically reason from the current weather conditions and the weather report on the internet and say it's likely to rain tomorrow, and here's your umbrella. How will it do it? It will first go through to the brain, figure out what the next action is here. The next action, as we see, is tool calling. So it will call the weather tool, figure out what the weather is like for today, tomorrow, and then what it's going to do is basically understand, okay, we need to figure out and give the umbrella. And because this is a actual agent, it will actually need perception and vision to be able to see and understand its environment as well. This is very futuristic work. This is not something I think currently exists, but is likely there in research. All right. The other thing that we really have to talk about when we talk about agents is design patterns. So there are multiple different design patterns. I've picked a few that I think are very critical. And actually, a few of these we will kind of expand on a bit more within my blog, Vinija.ai, in the coming weeks. The first one being reflection. Reflection is a very big area of research currently in agents, and this doesn't fully do it justice. Reflection could be its own hour-long lecture itself. So hoping to have a new primer out on that soon. And just, yeah, feel free to take a look at that as it comes out. But basically, what reflection is agents' ability to self-evaluate and iteratively improve their output. So as we talked before about base LLMs, is the base LLM was never able to kind of reflect on what it said, on what it output, and kind of fix its output iteratively through that. So if you remember the prior versions of maybe even ChatGPT, when you would ask for, say, a code snippet, it would be able to just give you something, but would you be able to guarantee that that code would work? Not 100%. But currently what it does is it has a reflection phase where it actually will do a call to a Python IDE, or it will do a basically and try to execute the code that it has written for you to make sure that there are no bugs there. And if there are, it will kind of go back and keep refining it before it gives you the full output. This makes the output actually more reliable than we had earlier. Now, reflection comes in many different forms. This was just for code. There could be reflection based on even answer truthfulness, groundedness, right? So, if you're asking for who is the president today in the US, it will, it can give you an answer, but it would need to, confirm through maybe multiple websites to make sure that it's able to give you today's current answer. What is the weather today? Just basically reflection also can help it not fully eliminate, but reduce a lot of the hallucination that the LLM system used to do earlier. Tool usage we saw earlier as well. Tool usage is basically integration with external APIs, searches, code execution, like I just mentioned. External APIs could be the weather API, maybe even a search API to be able to do multiple different search calls for your question. and just to be able to retrieve the right answer for you. It could also be maybe, you know, a call to a calculator to be able to, maybe you're looking for a calculation on your mortgage, depending on the interest rate today versus an interest rate tomorrow or so, and understand whether you should invest or not. You know, it could do a tool call to a calculator to be able to help give you that information and break it down for you. Planning, basically agents autonomously design structured multi-step strategies. So if you've ever used Cursor, it actually outputs the planning steps for you there, which is very interesting to see. So say you ask it to build just a simple website, it will first, you know, the steps could look like: one, understanding the requirements; two, you know, making sure that the UI has all of the details that it needs. Then it'll maybe start looking at different frameworks, integrate a login, integrate a database, but it will basically lay out each of the steps that it's looking to work on and cross it one by one as it's executing, very similar to how humans work, and you know, like crossing out to-do lists. Um, Multi-agent collaboration. So this is a very, very large framework of multiple different agents, and these could be specialized agents that work together on complex tasks. So maybe you have, you know, you come in and your system has a simple planner agent. Um, what you need is a very specific answer on, you know, something that is biology related. That agent can then kind of call this other agent that's been fine-tuned on biology specific data to be able to help answer your question even better. Or if it calls the biology data and the answer is not available there, then that agent can kind of take it from there and make a better educated guess on which tool to call, or which article to pull out from the vector database or the normal database to be able to kind of interpret the user's question, understand the answer, and get it back to the user in the most reliable way. So basically, what these patterns help us do is they help us enhance the adaptability, reliability, and scalability of our AI system. Do we need to have all of them for our system? No. It makes sense working backwards from what your use case is, what success looks like for your system, and then figuring out which component you should be sort of adding into your system and which you can kind of live without. So
One question
yeah, go
here.
ahead.
So you're talking about the multi-agent again. So there's two things that you can do, right? One is a sequence action, and there's a parallel execution that you can do. Is there a decision tree that when to select a sequential action or against a parallel? Because today I was reading in LinkedIn saying that somebody reported saying you're getting an unreliable output, so you're going with a parallel execution, whereas in the sequential execution, you're getting a reliable output. But Andrew and G discussed about parallel. That's an emerging pattern coming up with the parallel execution. So, what is your viewpoint on that?
Yeah, that's a very good point. And you can think of it like a decision tree. Basically, what the planner agent will do is, as it's looking to plan out the execution steps, it needs to understand dependency. So, if it can parallelize if there's no dependency on the prior tasks, right? If there's dependency on, so like we need to call a different agent, and once that agent outputs what that agent outputs, then we can take that to search into the vector database. We've defined a clear dependency here. So that has to be sequential. If it doesn't have to be sequential, if it's just looking for an answer and it's looking for any means to find that answer and then aggregate all of the answers to find the best fitting one for the end user, in that case, you can do parallelism. And how is this decided? How is this workflow decided? It's very similar to a decision-based tree in the backend, where as it's creating its plan, it's understanding the different dependencies and saying once task A is done, task B is dependent on task A's completion, so we have to wait on that. But say task C is very independent, so we can run task A, task C together, and basically execute the next steps as we kind of get to that. So very tree-based structure there. very use case dependent. There could be, some use cases that are very, yeah, dependent on the prior scenario that's run. In that case, we would have to stick to sequential. But parallel would give you the best scalability. Also, it could kind of expand and scale a lot faster than how we could. If we didn't have the system and we had to search for a research problem, we would just be limited by our abilities, where we can only, search Google once ourselves, look through each article ourselves, note down, okay, this article said that, that information said that, aggregate all of that information together. Whereas if an agent-based system was doing that, it can actually query and read through all of the articles at the same time, aggregate that information and have it back to you. So that's how parallelism kind of helps, especially in terms of these harder use cases, and it also helps scaling and speeding up our end process. Yeah. Does that kind of
So,
help?
yeah, is it like who takes the driver's seat in terms of like, do you have to do it? You have to give that instruction when you're designing that agent, or is it part of the like agentic framework like Chain or Crew AI or other
Yeah.
agentic?
Yeah. So I think your question is, how does the planning actually work? That's not something you do. That's how this is the way they run autonomously. So we'll talk about different function calling data sets and how to do eval on them. And so there's multiple different ways. One, you can take your planning agent and fine tune it. And I'll show you the data sets that you can create to use to fine tune your agents to help it understand that's something that's specific for your tasks. Second is you can add it to the system prompt. Say, you have these specific tools for any of these queries. We need these answers. A third way is kind of an iterative process. So, it comes back, say it only searched one Google link and it came back with the answer and it was not right. So the user says back, no, this is not what I want. I want a more detailed list curated. Then it will go back and execute. The last and I guess the most important step is refinement. We need to show the agent all of these use cases, especially ones that will occur more often, and have it execute through its system and run evaluations there. If it's not working per plan, then what we need to do is go back into our entire system, figure out where the breaking point is, and figure out if we need to maybe fine tune it further. If, what the next steps here are, maybe we need to refine its system prompt. Maybe its current system prompt says that when you're doing search, you only need to look at, one website. Tell it to actually look at multiple websites, do parallel calls, aggregate the best results. Maybe it's looking for, this happens often in industry too. Maybe it's looking to basically not have as much latency and get back to the user quickly, rather than get the right answer and do a deeper search. In that case, you want to kind of tell the agent that, no, we don't want to get back as quickly. We would rather have a more fully executed solution at the end, rather than a very quick call. So those are kind of the few steps, but basically if it was not executing per your priorities, I would start breaking the system down, evaluating and figuring out each of the different components that we needed to look at. And we'll talk about this as well. There's abstract syntax tree, which we can leverage to basically do that. And we'll get that at the last slide, I believe. Yeah, awesome. Okay, so going back to reflection then. Reflection workflow. Basically, the reflection is a very, very key part of the agentic system, and it goes back to your question as well. Because if it didn't execute the plan correctly, it needs to reflect and understand what went wrong. So the initial step would be the LLM generates a draft for the assigned task, and this draft is basically its plan of execution. The agent will then self-critique the output, highlighting the weaknesses or inconsistencies. And here you can have the agent itself, or you can have a different critiquing agent looking at the work of the initial steps and then critiquing it and telling it how to improve it upon its steps. Feed and then feedback is basically integrated into revised output for continuous improvement. And the cycle will keep repeating, kind of yielding to progressively refined and higher quality results. External tools can also be added here for fact checking, validation, any, verification that you can kind of have here to also help reflect and kind of help the agent critique and refine its processes there. So that's why reflection is a very, very key important research area that's growing out right now because it's very critical for agents improvement, and it's even not just improvement, but even the first initial outcome it gives, even the first initial plan it gives. It's very important to kind of critique it through and make sure we're able to give the end user the correct information and the best plan possible. And now to go beyond just self-reflection, agents, there's also multiple different things that you can do here. Basically, agents can use tools to quantitatively validate their output, like for math or coding. You can look at different, coding calls. You can look at executing code before having it as an output. Yeah, code evaluation. You can do unit tests too to make sure there's correctness, there's functionality, there's no hallucination of library calls, of different function calls. Text validation, you can leverage maybe internet searches, external database to do a lot of text validation. Feedback from tools can be integrated into iterative refinements. And basically, this will kind of help minimize a lot of the errors. So this is just, in core software engineering, a lot of the testing could be done with integration tests, unit tests, just figuring out how, where, or how the system is breaking. This because the agent is a black box and we don't have a clear understanding of how the internals are working and how we are getting the output planning steps that we are getting. We have to rely on a lot of these different components to be able to validate all of our execution calls and all of the different outputs that we are kind of seeing here.
Can I ask a question?
Yeah, absolutely.
So for something like reflection, like you
Yeah.
work for Google now, how big is your team like working on something like this?
Yeah, so this is more of a research-based problem. I can share offline if you'd like to. There's quite a lot of papers, not just out of Google, out of OpenAI, out of Anthropic, other companies that are looking into delving into this. It's a pretty big area, especially as companies are expanding out into using more agentic-based systems for a lot of the even internal and external tooling. um, it's a growing area. It's not a very production-based area though, so you won't see products out of it. It's more of a research-based area, so you'll see companies releasing more papers around it currently, if that helps answer your question.
Yeah, I think on Copilot now they can actually
Yes,
fix bugs.
yes,
So that's a form of self-reflection. I
yes.
just like take on something like this in like one of our project teams here on the campus. We
Hmm.
have 5 or 6 students. It seems like an impossible task. So I'm sort of interested on how you as a researcher at Google can take on something like this. Is it all compute based or your own AI tools, or are you actually writing code for things like this?
It's kind of a mix of all of it at once. So it really depends on first kind of, I guess I would have to go back and kind of explain how we work internally to or just as a researcher itself. So what we kind of break it down into is just a specific problem to chase. This is a very, very large problem and it can't solve everything at once. So kind of break it down into a simple hypothesis. Maybe the task is to do bug fixing, like you mentioned. How do we do that? So we will break down into several different components where someone may say, okay, maybe a prompt-based solution could work. Maybe refining the alignment phase, refining the RL phase could work. Figure out, which component here we should be chasing, and then kind of execute on that. Do a lot of internal checks, do a lot of testing there. And once we find like something that is executing well, something that is proving to be reliable on multiple different use cases, multiple different iterations, that's when you'll see a paper kind of out there as well. But basically what it is, it's a refinement of the actual LLM itself, whether it be on the pre-processing or the post-processing, likely more on the post-processing itself, which could include fine-tuning, which could include alignment, multiple different layers of alignment, maybe even multiple different layers of fine-tuning, or all of it combined at once. That's kind of what it looks like in terms of research.
Very good, thank you.
Yeah, absolutely. All right, so now we can kind of look into the tool uses in the agentic system itself. All right. So tools will take the LLM beyond its own capabilities and kind of help execute tasks in the real world. So agents are, are able to dynamically select tools like APIs or databases, web searches, financial calculations, email management, and just expand the LLM's practical utility across, different domains and different industries. So here are kind of the 5 levels of agentic AI systems. The first one, like we saw, could be a basic responder. A user comes in with a query, they prompt any LLM. Here we have DeepSeek, and then it's going to basically respond back to the user. This is a simple search use case. You looked for one thing, you got it back. 2 is the router pattern where we query, you get to the planner LLM and it's going to route to the different tasks and then get a response. The third is a tool calling. And here, as you can see, the tool calling could be a database, API calls, browser. You can even look at your local file system and get a response there. Multi-agent patterns too. So multi-agent patterns, you can have a query come in and a manager agent. The manager agent can talk to different sub-agents who can actually work in a collaborative fashion. So you can think of it of a software team maybe and how they work together, and how you have a manager kind of assigning tasks, and each engineer can chat with each other to understand, get more information. Maybe one person has more historical information on a specific code path and the other person is looking to execute on that, just find means to collaborate there and then get the end result. That's what a multi-agent pattern can kind of look like. And an autonomous pattern could just be, a user comes in with their query, they go to a generator agent that looks for a response, then it gets a validator agent to basically critique it and give feedback, and this loop can iterate on a few times and then give the final response. So these are just other kind of tool use designs of and different patterns to be able to kind of develop agentic AI systems as well. So now I wanted to kind of delve into a little bit more lower level details. So this will be function calling examples. And this is a very simplistic, just a quick pseudo-coded example here. Basically, this example, you're looking at web searches, integrate and retrieve current and up-to-date information. So you'll just have, a simple function here. It's just called web search, and it's going to return search results with the query that you have. Then you also have, say, another tool, calculate interest. You have your principal rate years, and it's just going to return a simple calculation. The agent will decide which function to call depending on the user query. If there's search in the user input, then it will go to the web search. If there's interest, then the user will go to the, calculate the interest. And it will contextually decide which tool to call. This is obviously a very simplistic use case. It's not going to be in an if-else, kind of scenario. What it's going to be more is contextually rich information with the agent has to semantically understand and to be able to translate that into different API calls that it knows that the system has downstream, and not just translate it into API calls. It needs to be able to do something called as slot filling, to be able to fill in the different parameters of the API calls based on the user's query. And the other complex thing that can happen here is API calls can have optional and multiple different kind of parameters within itself. The LLM needs to understand accurately which parameters, which slots to be filled into which function call. So that's where a lot of our eval and a lot of our data set curations will kind of kick in, and we'll see that next as well. But that's kind of an example of how function calling works. It's a little bit more complex down under the hood. And if the agent does hallucinate, it can cause downstream hiccups. So, you need to make sure that you have fallback use cases as well in the event that it doesn't have enough examples for that specific use case and it hallucinates a call that will give it the wrong results. For example, if you have say an Alexa device at home and you ask it to play Taylor Swift songs and it plays say another artist Beyonce songs or something else, that's an hallucinated call in the slot filling section where it misunderstood the artist's name, which gives the user a bad experience. So that's where the a lot of the eval and a lot of the training data sets have to be one, have to have enough examples for the agent to understand, and two, the eval needs to be robust to make sure we don't have hiccups like that for the end user. So here is the function calling data sets, and kind of one of the core pieces of the entire agentic system as well. So what is a function calling data set? A function calling data set is basically a collection of examples showing how the model should use functions, the tools, the APIs by generating structured JSON formatted outputs instead of plain text. So, instead of just writing words, like the model will need JSON like output that matches the tool's schema itself. Each of these examples, and we're going to actually look at the examples in the next slide, so don't worry about that. But basically, each of the examples teaches the model when and how to call the function. Data sets are used to, you can either train or you can even fine tune if you find that that just kind of training or just kind of having it in the prompt is not giving you the most accurate results. You can actually fine tune the model with your data set here, so it can reliably call your tools. And the different tool sets and the different data sets available here for function calling are Hermes data set. And all of these are available on Hugging Face. I definitely ask you to take a look at these. The Hermes, there's Salesforce, there's Synth, API Gen, and basically they benchmark on reliability, correctness, and tool integration accuracy. To give you an example of what it looks like I mentioned, it's a very it's in a JSON format, and what it does is it will have multiple different fields. So the first one will be the name of your function call. So for this, it's get weather. The second will be the arguments. So here, you just have simple location and date. This will actually be very extensive for real use cases. So you will need to give optional arguments. You'll basically need to give it all of the different variations that it can see for this specific API call. The more robust that your data set is, the better your agent will perform on this. And for what this is, it's basically giving you a skeleton. So this data set will give you a skeleton of what it expects. And it's up to you to fill out all of the, because your API calls and your tools are very specific to your system. So it's up to you to fill out all of these arguments in the correct way and make sure it has enough examples to make sure that your system is working accurately here. The next, and I guess the most important piece here is evaluation or evaluation of the function calling here as well. So firstly, we have the Berkeley function calling leaderboard. So you can search for it. I believe it's also available on Hugging Face. And what it is it's a public benchmark that ranks LLMs on their ability to generate the correct function calls. And when is this used? This is basically used to compare different models. So, you can have GPT, you can have Claude, you can have Llama. on the same tasks. And basically, you want to be able to see how well a model is able to generalize to new or complex function calls in different scenarios too. For researchers and developers, you can kind of, track the progress of how the different models are faring against each other by just kind of looking at the leaderboard itself. So that's one thing. And I would definitely look at that before starting development there. It also, measures accuracy, reliability, robustness of the function calling, evaluates performances in Python and non-Python environments with complex APIs. The next big thing is abstract syntax trees, and this is used for evaluation. This is basically mimicking the entire call process of your agent lifecycle. So it's a structured representation of the code or function calls, and this is done in the tree format. I believe we touched on this a little bit earlier. But what this is used, it's used to validate whether the generated function call is correct beyond just string matching. And it's basic. So to give you an example, if even if we're spacing or if a little bit of the formatting differs, AST can kind of confirm the arguments and the structure generally is correct. It's very useful for grading, function calling data sets and evaluating real world task execution. You can kind of, yeah, so basically you can think of it as helping to validate a lot of your output calls there itself. And together with both of these, with the Berkeley function leaderboard and AST, you can kind of build a very robust function calling downstream system. And this is the kind of the tree overview of how AST works. So what you'll give it is your function description, the different possible answers, the model output functions. It'll extract the function name, it'll extract the function itself, and check if there's a function match. If no, it'll tell you that there's a mismatch. If yes, then it'll go deeper and extract the parameters. If the parameters are wrong, then it'll fail there. Then it'll go a layer deeper and check if there's unexpected parameters. So then there was likely a hallucination. It'll go deeper and check if the parameter types match, because you can have, a type mismatch as well for your input. If so, it'll error out. Once its type is matched, then it'll go even deeper and check, do a string checker, a list checker, optional value checker too, and check if the values fully match. Otherwise, it'll error out or it'll just say it's a valid call. So this is one very, very structured way to evaluate just the function calling portion of your agent framework. And this is actually used quite often as well in research and industry. So yeah, I've covered a lot of ground here and a lot of information. Wanted to kind of pause here for questions. And secondly, also wanted to share all of the material I've covered here today is available either on my website, Vinija.ai, or Aman.ai, my husband's blog. And feel free to scan it. There's a lot more detail, a lot more links, and a lot more research papers that are covered in the blog that I'm not able to pull in to an hour-long lecture. So I definitely urge you to, take a look at all of the content there. But yeah, happy to take any questions now.
What's a day in your life like today?
Yeah, so day in the life really varies based on, what I'm doing. Today's going to be a very code intensive day and a lot of evaling and a lot of kind of checking in projects and kind of landing them. I'm sorry, I'm not able to really speak concretely about a lot of the stuff just because it's not out yet. But that's kind of what my day is going to look like today. It's going to be quite a lot of just within collab notebooks. Most days are like that, and that's kind of what I enjoy. Other days are also very, collaborative, sharing different work and outputs and learning from each other as well. Yeah.
Well, fantastic. I think we got a very very good overview and a good starting point. I think few people engaged here are actively coding or developing agent-based systems. So I think they will be able to compare notes. For others, this was very good introduction. Thank you very much, Vinja. And we have Vinja's AI website and email. If you guys want to reach out, feel free to do so, or talk to Venkatesh, and we'll get the answers to your questions. All right. Thank you very much.
Thanks, Dr. Shade. Thanks, everyone.
Thank you.